sciences, and I'm going to talk about introduce you to machine learning using Scikit-Learn. So let me share my screen. So in this workshop, we assume that you know close to nothing about machine learning, and our goal is to introduce you to the jargon of machine learning and also some concepts which help you to start learning machine learning. And we will cover a few techniques from simple linear regression to the decision trees and random forest. And instead of implementing the method by ourselves from scratch, we will implement Scikit-Learn's implementations, which is very efficient. And so instead of preparing a PowerPoint for this workshop, I decided to prepare a couple of notebooks. So you have access to the notebooks on my GitHub page. So if you click on this link on the Hack MID under ResBazAZ 2021, there are a couple of notebooks, ResBazAZ 1 and ResBazAZ 2. Hopefully we will have enough time to go over both of them, but we will start from ResBazAZ 1. Just let me know if you have a problem accessing these files. And also during the presentation, please stop me whenever you have questions. So as I mentioned, does anyone have access to the notebooks? Okay, cool. And also you can either download the notebooks and run it on your local machine. Also, there's a button here to run on Colab. If you click on that, you will be able to run it on Google Colab, which is much easier, I guess, compared to running on your local machine. Okay, so let's start. As I mentioned, the objective of the workshop is to introduce you to machine learning concepts using Scikit-Learn. And for the prerequisite, I assume that you are familiar with Python programming language, and also you have experience working with scientific libraries of Python, such as NumPy, Pandas, and Matplotlib. And also you should have a little mathematics and probabilities background in order to understand what is under the hood. And in this workshop, first, we will try to understand what is machine learning, what are the problems that machine learning can help us to deal with, what are the main categories of machine learning, what are some of the fundamental concepts of machine learning. Then we will try to see what are the main steps for doing a machine learning project. Then we try to fit a couple of machine learning algorithms to existing data sets. And finally, we will try different models such as linear regression, decision trees, and random forest. So in addition to this workshop, which is, I think, is a good starting point for getting into the continent of machine learning, we have lots of sources online, which includes the Andrew Ng's ML course on Coursera, which is amazing, but it takes a lot of time to watch the course, maybe a couple of months. In addition to that, the Scikit-Learn has an exceptional user guide. You can start reading that. Just let me show you. The user guide, the tutorial is amazing. Everything has been clearly explained. There are a bunch of examples there. You can go line by line and learn a lot of things about machine learning. There are also a lot of websites like DataQuest or Kaggle, which have a lot of blog posts about machine learning. Zoom in a little bit. What do you mean? Kelsey, can you please what do you mean by zoom to this one, to the notebook? Is it better now? Okay. So in addition to the DataQuest, blog post on Quora, and also Kaggle, there are a lot of books available. Personally, I have read these two books, which are amazing starting point for learning machine learning. The first one is Joe Gross's Data Science from Scratch, which is published by O'Reilly. And the other one is Stefan Marsland's Machine Learning and Algorithmic Perspective by Chapman and Howell. which both of them are really good points to start the machine learning. But first, let's start by some fundamentals of machine learning. So most of the people, when they hear about machine learning, they picture a robot or a deadly terminator, but actually machine learning is not something like that. Machine learning actually, in the simplest word possible, is an action to learn, the action to try to learn from data by programming, by reading programs. And machine learning has been available for several decades, and applications of machine learning has been around at least from 1990s. The spam filters is probably the most famous one. And it has been followed by hundreds of machine learning applications that we are using almost every day, like Alexa by Amazon or Siri in your iPhone. And there are hundreds of machine learning algorithms which are available out there and we are using in our daily life. We will quickly talk about different categories of machine learning, from supervised and unsupervised learning methods, online versus batch learning, instance-based versus model-based. And then we will talk about fundamental concepts and jargon of machine learning. And these are some concepts that you need to know by heart if you are trying to be a data scientist. So these are really important concepts, so please stop me whenever you have questions. And let's just start by definition of machine learning. So machine learning is defined as the science and art of programming computers so they can learn from data. And a more general definition is provided by Arthur Samuel in 1959, which defines machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. And maybe a more engineering-oriented definition is that a computer program is said to learn from experience E with respect to some task T and some performance measure P, and its performance on T is measured by P and improves by experience E. So the spam filter is a very famous example. I will use this example several times during the presentation. So the spam filter is a machine learning program that, given examples of spam emails that are flagged by users and examples of regular emails, non-spams or simply ham, it can learn to flag the spams. And these examples that the system used to learn are called the training set, and examples in that training set are called training instances or samples. In this case, the task that we are trying to solve is to flag spams for new emails, and the experience is the training data, and the performance measure P needs to be defined. But for example, this is a classification task, and for classification task, we usually use a matrix which is called the accuracy, and that's simply the ratio of correctly classified emails. And why we need to use machine learning. So if we try to use traditional programming techniques to write a program for classifying emails, first we need to consider what an spam emails typically look like. And for this purpose, we may notice that there are some phrases like "for you," "credit card," "free," "amazing," that appear a lot in the subject line of those emails. And then you may try to find another patterns in the sender's names and stuff like that, the body of the email. And then you need to write an algorithm which is able to detect these patterns and flag an email as a spam if number of these patterns appear in that email. But as you probably noticed, this is a very tough task. So it is very difficult to implement something like this. And you need to hard code everything in order to launch this program. On the other side, when you are using machine learning, the machine learning technique can automatically learn from word and phrases that appears in the emails to filter an emails as a spam or ham. And just consider the case that the spammers learns what you have banned and flagged as spam emails, and they start to changing, for example, "for you" to "for you." And if this happens, you have to hard code everything again. But when you are using machine learning, you don't have to hard code everything. And the machine learning is able to automatically learn what patterns are frequent in spam emails again and try to filter them out. Another area which machine learning shines is for problems that are too complex, and our traditional approaches are not really good to deal with these problems, or we don't have any traditional algorithm to solve the problem. So for example, consider the case of speech recognition. When we try to write a code to detect words, we need to write a code to detect the words 1, 2, and there are thousands of words that we need to hard code in order to be able to do that. But with machine learning, it's much easier. The NLP, natural language processing algorithm, have developed a lot, and we just need to provide them enough instances so they be able to do the task for us. And also machine learning can help us to learn. Machine learning can be inspected to see what we have learned. And for example, I gave you an example of the spam filter for the emails, but there are much complicated tasks which machine learning can help us to extract the information from the data, and by exploring the decision rules for the machine learning, we can gain insight about what is under the hood. So to summarize, machine learning is great for problems for which existing solution requires a lot of fine-tuning or long list of rules, complex problems for which using a traditional approach yields to no good solutions, and when we have fluctuating environments like the spam example, and when we are interested to getting insight about complex problems and large amounts of data, which falls into the category of data mining. So there are different types of machine learning systems. Some of the machine learning algorithms can be categorized based on the fact that they are trained with human supervision or they are not. So this is called supervised versus unsupervised learning. Another categorization is based on the fact that whether or not the machine learning can learn incrementally on the fly, which defines online versus batch learning. Another category is based on comparing new data points to the existing data points, or whether we try to learn a new model, and based on that, define our method, which includes the instance-based versus model-based learning. And these criteria are not exclusive. We can combine them. For example, we can have deep learning model for spam filters, which is online, model-based, and supervised learning. So supervised learning, in supervised learning, the training sets we feed to the algorithm include the desired solution, which are called labels. So this picture shows that we have some emails, we got the labels for them, whether they are spam or ham, and then we train the model using this training set. When we have a new instance, we ask the model to categorize this email or predict this email, and it will tell us whether it's spam or ham. This is a classification example. We can also have regression examples. So in the regression, the target is to predict a numerical value, such as the price of a car, given a set of features like mileage, age, brand, etc., which are called the features or predictors. These sort of tasks, as I mentioned, are called regression. And in the regression task, so we got a feature, we got a target or value we are interested to predict, then we find a relationship between this data, and then use that relationship to predict new instances. So here I have listed the most important supervised learning algorithms: k-nearest neighbors, or KNN, linear regression, which we will cover, logistic regression, support vector machines, or SVMs, decision trees and random forests, which we will cover if we have time in the second part of the workshop, and also neural networks. So on the other hand, we got the unsupervised learning. And in unsupervised learning, as you might guess, the training data is unlabeled. The system tries to learn without a teacher. And we also have a category which falls between unsupervised and supervised learning, which is called semi-supervised learning. And since the labeling of the data is usually time-consuming and costly and sometimes not possible, we've got plenty of unlabeled instances and a few labeled instances, and there are a few machine learning algorithms which can deal with partially labeled data, which are called supervised, semi-supervised learning algorithms. So we don't have enough time to cover unsupervised and semi-supervised learning algorithm in this workshop. As I mentioned, we also have a category based on whether that model is batch learning or offline learning or online learning. In batch learning, the system is incapable of learning incrementally. It must be trained using all the available data. And this will generally take a lot of time and computing resources. So it's typically done offline. As I mentioned, it's called also offline learning. And first the system is trained and then it's launched into the production and runs without learning anymore. And it just applies to what it has learned. And in online learning, the system is learning incrementally by feeding the data sequentially, either individual data or a group of small amounts of data, which are called mini batch or batch. And each learning step is fast and cheap, so the model can learn on the fly. So deep learning models usually falls into this category, and classical machine learning algorithms like linear regression, decision trees, and random forest falls into the category of batch. So, and finally, instance-based versus model-based. So possibly the most trivial form of learning is simply to learn by heart, to memorize the examples in our mind. And if we are able to create a spam filter this way, it would be just flagging all emails that are identical to emails that have already been flagged by the user. This is not the worst solution, but probably not the best. Instead, we can just flag emails that are identical to known emails, and your spam filter could be programmed to flag these emails that are very similar to known spam emails. And this requires measures of similarity between two emails. A very basic similarity measure between two emails could be to count the number of words they have in common. The system would flag these emails as a spam. If it has many words in common, then the other email can also be considered as a spam. This is called instance-based learning. The system learns by examples by heart, and then generalize to new cases by using a similarity measure, compare them to the learned examples or subset of them. So for example, here we got a class which are yellow squares, we get another class which are green triangles, and then we have a new instance here. It starts to measure the distance to this, the distance between this instance and other distances which are close to it. And then based on that, the model can tell us whether this is a green triangle or a yellow square. So the most famous method which uses this kind of technique is k-nearest neighbors, or KNN. Another way to generalize is to learn a relationship or build a model from the examples provided to the machine learning algorithm, and then use that model to make prediction. This is called model-based learning. So here, again, the example of triangles and squares, you can see that the model has learned this line which separate the triangles and squares, and when we introduce a new instance based on the location of that instance, the model can tell you whether this is triangle or squares. So I have provided an example here. Suppose you want to build a model to tell you if money makes people happy or now. So you download the Better Life Index data from OECD's website, and we got also the gross domestic product per capita from IMF websites. Then we join this table. So for each country, we got the GDP per capita and also Better Life Index, and we want to write a function or build a machine learning algorithm to help us to predict the Better Life Index, BLI, based on the GDP. So for this purpose, let's import the Scikit-Learn library first. I have created the functions to read the CSV files that we can download from these websites and join them. So you just need to run these cells, and this is the part which you need to know numpys and pandas. And following table, which is here, after running this cell, you can see that the name of the countries, GDP per capita, and life satisfactions are provided. So each of these rows in this table are instances that we are going to feed to the training, to train the machine learning model. And I have plotted the data here. So the x-axis shows the GDP per capita, the y-axis shows the life satisfactions, and each of these circles shows a country. And when you look at the line, look at the instances, you realize that it's very close to a line. So maybe a linear regression is not a bad choice for this, but we will discuss this later on. So also the data is noisy, as I mentioned. It looks like that the life satisfaction goes up more and less linearly as the country's GDP per capita increases. So we decide to model life satisfaction as a linear function of GDP per capita. This step is called model selection. And we select a linear model of life satisfaction with just one attribute, which is GDP per capita. So based on this linear relationship, which is life satisfaction is equal to theta 0 plus theta 1 multiplied by GDP per capita, our model has two parameters, theta 0 and theta 1. And by tweaking these parameters, we're going to make your model, make a model that represents the data in this data set. So I have randomly set parameters for this, for theta 0 and theta 1. And the green line shows one of the trials I have. The red one shows the other trial I had, but none of these lines are really good. So before we can use our model, we need to define the parameters theta 0 and theta 1. But how can you know which values will make your model perform best? So the answer to this question, we need to define a performance measure. So we can either define a utility function or a goodness of fit function that measures how good our model is. Also, we can define a cost function, which measures how bad our model is. And for linear regression problem, people typically use a cost function to measure the distance between the data points and the predictions of the model, which is the line, and then try to minimize this value as the cost function. So this is where the linear regression algorithm comes in. We feed the training examples and it finds the parameters that make the linear model fit best to your data. This is called training the model. And in our case, the algorithm finds that the optimal parameter values are theta 0 equal to 4.85 and theta 1 equal to almost 5 multiplied by 10 to the power of -5. So for your first machine learning model, now we're gonna try the linear regression to find these values. What we need to do is to import the linear model from Scikit-Learn. Then we create an instance from the linear model. This is called the linear regression. And then we need to define our X and Y. Our X is the GDP per capita, as we discussed here in this formula. And our Y is the life satisfaction. We define X and Y, and then we call the fit method from that instance and fit the X and Y to that. And then if you run these cells, we can call the intercept and also the coefficient in order to get those values. And as you can see, these the intercept and the slope are exactly numbers provided here. And if we plot the line, we see that the line exactly passed through our data. So we are now ready to run the model to make predictions. So for example, say we want to see how people of Cyprus are, but the OECD data set doesn't have the answer to that. Fortunately, we've got now a model. We can feed the GDP of the Cyprus to the model, which is $22,500, almost $500. And then when we apply the model, we can calculate the life satisfaction index equal to 5.9. So this is the plot which shows that. So the GDP of Cyprus is almost 22,000. If you connect it and find the corresponding line, a corresponding point on the line, that's equal to 5.96 on y-axis, and that's the life satisfaction for this Cyprus. So if everything goes correct, now our model is able to make good predictions. If not, we need to use more attributes like employment rate, health, air pollution, etc., to get a better estimation of the training data and life index, better life index, or perhaps to select the more powerful models like the polynomial regression model. So what we did here in the simple linear regression problem was to study the data, select the model, which was linear regression. We trained the model using the training data, and finally we applied the model to make predictions on new cases. In this case was the predicting the better life index of the Cyprus. And this is exactly what a typical machine learning project looks like. We got a bunch of data, we need to select the model, train the model using those data, and at the end make predictions based on the model. So far we have covered the ground for machine learning. What is machine learning, why it's useful, what are some most common categories of machine learning, which were supervised versus unsupervised, instance-based versus model-based, and batch versus online. And we looked at the workflow of a typical machine learning project. Now we're gonna look at what can go wrong when we are learning and what prevents our method from making accurate predictions. So these sections are called main challenges for machine learning. In short, since our task is to select the learning algorithm, train some data, two things can go wrong. We can have bad data and we can have bad algorithms. So we will start with bad data, what we mean by bad data, and then we will see what bad algorithm means. So the first thing that mean by bad data is insufficient quantity of training data. So for training almost all of the machine learning algorithm, we need a lot of data. But compare it with the case that we are trying to teach to a toddler the word apple. What we need to do is to point to an apple and say apple and repeat this process several times. And the kid or child will learn to recognize apples in all sorts of colors and shapes. But machine learning is not quite there yet. As I mentioned, it needs a lot of data for most of the machine learning algorithm to work properly. Even for the simpler ones, we need thousands of examples. For much complex ones like the natural language processing, NLP, we need millions of examples. And other things that can make our model not able to predict very good values for our predictions is non-representativeness of the training data. So in order to generalize well, it is really crucial and important that our training data be representative of new cases. You want to generalize to, and this is true whether you use instance-based learning or model-based learning. So for examples, we got a set of countries. As I mentioned here, we got a bunch of here, but assume that there were some missing values there. And I have plotted those missing values, 6 more countries: Brazil, Mexico, Chile, Norway, Switzerland, Luxembourg. So if you train your model on this data, you get a solid line, while the old model is represented by the dot line. As you can see, not only does adding a few missing countries significantly alter the model, but it makes it clear that such a simple linear model is absolutely never going to work well. And it seems that very rich countries are not that much happier than moderately rich countries, and conversely, some poor countries are happier than many rich countries. So the data which we use for training at the beginning was not representative of these rich countries which are not happier, and these poor countries which are happier than the normal data provided in the training set. So by using a non-representative training set, we train a model that is unlikely to make accurate predictions, especially for very poor and very rich countries. It is also crucial to use a training set that is representative of the cases you want to generalize to. This is often harder than it sounds, and if it's sample is too small, you will having sample noise. But for the very large sample, can also be non-representative, and this is what is called the sampling bias. I have provided a couple of examples for the sampling bias here. One of them is related to the presidential election 1963, and one of the organizations were trying to predict the output of the election, but because of the sampling bias, they were not able to. And also another example, which you can read through. Another typical problem with bad data is poor quality data, when there are a lot of errors, outliers, and also noises into our training set, which will really make it hard for the system to detect the underlying patterns. So the system is less likely to perform well. It is often worse to effort to spend time to clean up your training data. And actually, most of the time when I use machine learning and deep learning myself, I spend like 80% of the time for preparing the data set that will be used for training deep learning and machine learning algorithm. So for cleaning the data set and preparing the data set, there are a bunch of things that we need to do. One of them is that if there's some instances that are clearly outliers, we may simply discard them and try to fix the error manually. Or if there are missing values in our features, we can decide whether we want to ignore the attributes or ignore the instances or fill in the missing values, and then try to train our model based on that clean data set. Another issue with bad data is irrelevant features. As the saying goes, garbage in, garbage out. Our system is only capable of learning if the training data contains enough relevant features and not too many irrelevant ones. So when it comes to the machine learning model, we should do something which is called the feature selection, that is selecting the most useful features to train our model with. Another thing is to do the feature extraction, that is combining existing features to produce more useful ones, which is called the dimensionality reduction as well. And also we can create new features by gathering new data. And these are the main categories of what we mean by bad data. So I will quickly review again. We should have enough data. Our data should be representative of what our model should predict in the future. We shouldn't have a bias in our data set. Quality of data should be good. And by quality, I mean there should be no outliers, and there should not be noise in the data set, missing values and stuff like that. And also we should use features or predictors that we think are really useful for the task we are dealing with. But we talked about bad data. In addition to that, we should also talk about the bad algorithm. And what we mean by bad algorithm is that the most important one probably is overfitting. And let's give you a picture about what I mean by overfitting. So imagine that you are within a country and the taxi driver rips you off, and you might be tempted to say that all taxi drivers in that countries are thieves. But this is definitely overgeneralization, right? We exactly have the same problem in machine learning jargon, which is called overfitting, and it means that the model performance on training data is much higher than its performance over test set. So I have provided an example here. This is exactly the same sets we were using, the predicting life satisfaction index based on GDP. And at first we were trying to feed a linear model to that, right? If I set the degree of the polynomial I'm feeding to this model to 1, we can see that it has a relatively acceptable performance. If I start increasing the degree of freedom, which kind of shows the number of parameters that the model have, you can see that for polynomial of degree of 2, the performance is still acceptable. If I go to 3, it is still acceptable. And if I increase up to like 60, the model is trying to fit to every single data points in this data set. While we know that this is not a good choice, because the model is trying to learn the noises in the data. So
To summarize, complex models such as deep neural networks can detect subtle patterns in the data, but if the training data is noisy, like the case we have here, or it's too small that the model cannot generalize well, then the model is likely to learn the patterns in the noise instead of the data. So another example could be that, okay, if you have a series of countries like New Zealand, Norway, Sweden, and Switzerland, and all of them have a life satisfaction index which is greater than 5, greater than 7, then you would generalize or overgeneralize and say, okay, all the countries that have a W in their names will have a life satisfaction index greater than 7. But there are a lot of poor countries like Rwanda and Zimbabwe which doesn't obey these rules. So this is something that is called overfitting. So we should avoid overfitting in our data set. And whenever we have a overfitting problem, and again, I repeat that when the performance of the model on training set is much higher than your performance on your test set or development set. So you can simplify the model by selecting a model with fewer parameters, as we saw here. Instead of a polynomial of degree of 60, we can use a degree of 2, 1, and 3. We can gather more training data, and also we can try to reduce the noise in our data to like removing the outliers, relabeling the data. And in general, constraining a model to make it simpler and reduce the risk of overfitting is called regularization. So for example, in the linear model we have 2 parameters, theta 0 and theta 1. This gives the learning algorithm 2 degrees of freedom to adapt the model to the training data. And the theta 0, the intercept, with the height, and the slope is defined by the theta 1 of the line. And if we force theta 1 to 0, the algorithm would have only 1 degree of freedom and would have such a hard time to fit the data probably. All it could do is to move the line up and down as close as possible to the training instances, so it would end up around the mean of the data set. So it becomes very simple model. If we allow the algorithm to modify theta 1, but we force it to keep it small, then the learning algorithm will effectively have somewhere in between 1 and 2 degrees of freedom, and it will produce a model that is simpler than 1 degree and 2 degree of freedom, but more complex than 1 degree. So we always should have a balance between feeding the training data perfectly and keeping the model simple to avoid the overfeeding and also have a good generalization of our model. So I have provided an example here again. This is the same data set. If we use a linear regression and use only the circles, which are countries with normal better life index, we will have the linear model, which is shown by the dotted lines. If we use all the data, including the squares, the red squares, we will have this guy, the red line. And if we use only the circles, blue circles, and use a regularization parameter, we will get the blue line, which is performance acceptable. So the amount of regularization is usually controlled by a hyperparameter, and a hyperparameter is a parameter of the learning algorithm, not the model, and it's not affected by the learning algorithm itself, and it is set usually before the training, and it stays constant during training. So if we set the regularization hyperparameter to a very large value, we will get almost a flat model, as I showed here, and I will tweak this parameter. And if we set it to very small value, it doesn't change the model that much. And let's tweak this hyperparameter here. This is again a simple linear model, but it is called the reach, and it has a hyperparameter which is called alpha. Here I have set alpha to 10 to the power of 9.5. If I set it to 5, which is smaller compared to 10, you can see that the blue line kind of falls over the dotted blue line. And if I start increasing the value of alpha, you can see that it starts to deviate from this line, and probably the regularization of this model will increase.
But if I set this value to a very large number, like 50, you can see that it seems like it's getting the average of these values and it's over generalizing the data. So that's why it's called the hyperparameters. You should tweak it. You should try different values for the hyperparameters and then find the best value. Another issue with bad algorithms is called underfitting the training data. And as you may guess, underfitting is exactly the opposite of overfittings. It occurs when your model is too simple to learn the underlying structure of the data. For example, for a linear model of the life satisfaction is prone to underfitting. The reality is much more complex than that. So our predictions are kind of inaccurate. What we can do in order to deal with underfitting is to select a model which is more powerful, has more parameters. We took the degree of polynomial, if you remember a few minutes ago, so we can increase the degree of polynomial. Another way is to feed better features to the learning algorithm, which is called feature engineering. So instead of the GDP itself, we can provide also the employment rate, health, pollution, and stuff like that, which we think are connected to life satisfaction. And also, we can reduce the constraints on the model or reducing the value of the hyperparameters for regularization, which we already did, and we saw how it will impact the results. So we talked about a lot of grounds in machine learning, and now I think you may feel lost, so it's a good idea to step back and review what we talked about. We said that the machine learning is about making machines to get better at the task by learning from data, and instead of hard coding the rules. There are three categories of machine learning algorithms in general: supervised versus unsupervised, online versus offline or batch learning, and instance-based versus model-based. We talked about the typical steps in a machine learning algorithm, which starts with gathering data for training sets, feeding the training data to your machine learning algorithm. If it's model-based, it will tune some parameters and feed a model to the data. If it's instance-based, it will learn by heart, define a measure of similarity, and try to classify or predict a value for our target. And finally, we said that if the training set is too small, if the data is not non-representative, and if it's noisy or polluted with irrelevant features, our model is not able to learn. And finally, our model should not be too complex to lead to overfitting, and it should not be too simple to cause underfitting. There's also just one more thing I'd like to talk, and after that we will take a short break and came back with a practical example for machine learning. So we're going to talk about testing and validation sets. So the only way that we know how well a model will generalize to new cases is actually to try new cases on our model. So one way to do that is to put our model in production and monitor how it performs, but it will cause a lot of problems and the user of our systems will have a lot of complaints about that. There's another option available, and that's to split our data into training set and test set, and then measure the value of the error or the value of the cost function over the test set, which is called the generalization error. And we should select a model that has a very good value of generalization error. I mean, but good value is a low value of the generalization error. So if the training error is low, but the generalization error is high, it means that the model is overfitting. As I mentioned earlier, if both of these errors are really high, it shows that the model is underfitting. And in practice, people usually use 80% of the data for training set and hold 20% of it for testing. However, it's very, very depends on the size of our data sets. If we have millions of training examples, if you set aside like 1% or 2% of the data set, that would be more than enough for training the model. And also, as we
saw a little bit earlier, there are some hyperparameters which are not part of the model, but we need to test different values for these hyperparameters and then select the best value. So evaluation of a model is simple enough. Just we can use a test set, but suppose that we are kind of hesitating between two models, linear model, a polynomial model. So how we can decide which one to choose? So for this purpose, a common solution is to what is called a validation set. We simply hold out a part of the training set and evaluate several candidate models on this set. And then the model with best performance of this on this validation set or development set will be chosen. And we train the model multiple times using various hyperparameters to reduce the training error and the validation error. And then we can launch this method. There's also another solution which is called cross-validation. And that's because when the validation set is usually too small, so the model evaluation will be relatively imprecise. So instead of selecting a suboptimal model, what we can do is to divide our training set into several sets, and at each time select a part of this training set for training and using the remaining data for validation, and repeat this process randomly several times, and then use the average of that for predictions. The advantage of cross-validation is that the performance of the model which we are selecting will be higher, but the downside is that the training time of the method will be multiplied by the number of validation sets. And finally, the last but not the least things is the no free lunch theorem. The simplest definition is that there is no best model available that you can use for every machine learning task. So what we should do is to try different models and then try to figure out what is the best model. So for this purpose, we got a data set. We split that into training set, test set, and also the validation set. We try different models on training sets. We evaluate their performance over the validation set, and we choose the best model based on the performance of the validation set. Finally, we evaluate the error on the test set, and then we can launch our model. So this is the very short introduction to the jargon of machine learning. In the next part of the workshop, we will talk about a practical example. We will use California housing price data sets and try to use a linear regression, decisions tree, and also random forest to predict the values of the houses in California based on a series of features. But before that, we will take a short break and we will come back in 10 minutes to continue our workshop. Thank you.
So welcome back to. So in the first session, we reviewed some concepts, and now we are going to have practical examples that help us to learn those concepts practically. Any questions? So we will continue. In this part of the workshop, we will look at the example project end-to-end, and the main steps that we will walk through are looking at the big pictures, that is mainly plotting the data and see, get the data, discover and visualize the data, and gain insight about it. And then we will prepare the data for the machine learning algorithms. And at the end, we will select a couple of models and train those models using the data that we provide. So it is always a good idea to work with real data when you are applying machine learning algorithms. Artificial data sets are really good, but as I mentioned in the previous parts, there are always a lot of noise and things like that in the data sets that you have to learn how to deal with them. So working with real world data is really recommended, and there are thousands of open data sets available in different fields. And the most important sources for getting this data includes the University of California in Irvine machine learning repository, Kaggle datasets, and Amazon's AWS datasets. So you can easily Google them. And when you open the website, you just search for the field you want. So for example, if you work with remote sensing data, you just need to search for the keywords remote sensing, and you can easily find a lot of information up there. So for this example, we are going to use the California housing prices data sets from Scikit-Learn repository. This data set is based on data from the 1990 California census. It is not exactly recent, but it has a lot of good qualities for learning, and we will pretend it is a recent data. For teaching purposes, I have also added a categorical attribute. I've removed a few features to make it easier for you to follow the workshop. So for this purpose, first we need to import a couple of libraries. We check the version of the Python. We import the Scikit-Learn and use the version method in order to check the version of the Scikit-Learn. We import the NumPy, import the OS, and also Matplotlib in order to prepare some plots. So the first step is to get the data and download the data. So please do not hesitate to follow up with me, and please stop me whenever your code is not working or you have questions or anything is unclear to you. The notebooks, as I mentioned, are available on my GitHub page here. If you click on the link under ResBazAZ 2021, there are 2 Python notebooks. We went over the first one in the first part of the workshop, and now we are talking about the second notebook. Anyway, so I have prepared a function in order to download the data. To download the data, the link is provided. The path to save the data is also provided. So you just need to click on this 3 cells, and the data set which you are going to use will be prepared. This is the data frame. I have called it housing, and using the head method, I have provided the first few rows of this data frame. Each row represents a district in the California. There are 10 attributes, including longitude, latitude, housing median age, total rooms in that district, total bedrooms, population, households, median income, median house value, and ocean proximity. So you can call the info method on the data frame, and it's useful to get a quick description of the data, in particular, the total number of rows, each attributes types, and also the number of non-values. So if we call the call the info method on housing data frame, you get this output. It shows that there are like 20,640 instances of the data set, which means that it's fairly small in the standards of the machine learning, but it's a perfect example to start. Also notice that there are, for the total bedrooms attributes, it only has 20,433 null values, meaning that there are like 207 districts that are missing these features, and we will need to take care of this. We will discuss this later on in more details. The data types provided for these features are numerical, except the ocean proximity, which is an object. So it could be any kind of Python object, but since you loaded this data from the CSV file, you know that it must be a text attribute. And when we look at the top 5 rows, you probably notice that the values in the ocean proximity columns were repetitive, which means that it's probably a categorical attribute, and you can find out categories exist and how many districts belong to each category by using the value counts on the value count method. So you just need to select the data frame, call the column, and then call the method value counts. And as you can see, there are like 9,000 districts, which the distance to the ocean is less than 1 hour. There are 6,500 inland, 2,500 almost near ocean, 2,200 near bay, and islands are 5. Now let's look at other fields. The describe method shows a summary of the numerical attributes. So you just need to call the describe over the data frame that we have created, and the count, mean, and also max. These are self-explanatory, that null values are ignored. So for example, the count of total bedrooms is 2433, not 640. The std row shows the standard deviation, which measures how dispersed the values are. The 25th, 50th, and 75th rows shows the corresponding percentiles. The percentile, as you probably know, indicates the value below which a given percentage of observation in a group of observations fall. For example, for 25 percentile, indicates that the districts have a housing median age lower than 80 here, while 50% are lower than 29 and 75% are lower than 37. These are often called the 25th percentile, median, and 75th percentile. There's also another quick way to get a feel of the type of data you are dealing with, and that's to plot each numerical attribute. A histogram shows the number of instances on the vertical axis that have a given value range on the horizontal axis. And you can either plot this one attribute at a time, or you can call the method heath on the whole data set, the data frame. And actually this code example does that for you. If you click on the run, we can see that histogram for each of the attributes and data sets are plotted: longitude, latitude, housing median age, total rooms, total bedrooms, population, median house values, households, and median income. There are a few things that you might notice in these histograms. First, that the median income attribute doesn't looks like it's expected in US dollars. The data has been scaled and capped at 15, actually 50,000.1. And for higher median incomes and at 0.5, actually 0.5. For lower median incomes, and the numbers represent roughly 10 of thousands of dollars. Working with pre-processed attributes is common in machine learning, and it is not necessarily a problem, but you should try to understand how the data was computed. If you look at the housing median age and the median house values, they are also capped. The latter may be a serious problem since it's your target attributes. Your machine learning algorithm may learn that pieces never go beyond that limit. You need to check with the team that will use the system, your outputs. And if this is a problem, you should try to deal with that. And if you tell you that you need the precise, the precise predictions, even beyond the 500,000, then you have two options. The first option is to collect proper labels for district whose labels are capped. The other one is to remove the districts from the training set and also from the test set, since your system should not be evaluated poorly if it predicts values beyond 5,100. And also, if you look at the histogram, you notice that these attributes have very different scales. And finally, many of the histograms are tails heavy, and I mean, they extend much farther to the right of the median than to the left. And this may take a bit harder for some machine learning algorithm to detect the patterns in the data. So hopefully now you have a better understanding of what kind of data you are dealing with. And next step is to create a test set. It may sound strange to voluntarily set aside part of data that we have. After all, you have only taken a quick glance at the data, and surely you should learn a whole lot more about it before you decide what algorithm to use. But our brain is an amazing pattern detection system, which means that it is highly prone to overfitting. So if you look at the test set, you may stumble upon some seemingly interesting pattern in the test set that leads you to select a particular kind of machine learning model when you estimate the generalization error using the test set. Your estimates will be optimistic, and that is not what we want. So this is called the data snooping bias. Scikit-Learn provides a function for this purpose to split the data set into multiple subsets in various ways. The simplest function is train test split. First, there's a random state parameter that allows you to set the random generator seed. Second, you can pass it multiple data set with identical number of rows, and it will split them using the same indices, which is really useful if you have different data frames for labels and also for your features. So in order to use the train test method, you simply from sklearn.model selection import train test split, then train set and test set are equal to train test split. You pass the data frame to it, you set the test size and also the random state. So you simply click on the run and it will be run. Next step is to discover and visualize the data in order to gain insight about it. So far, we have only taken a quick glance at the data to get a general understanding of the kind of data you are manipulating. Now the goal is to go a little more into depth. And first, we need to make sure that we have put aside the test set and you are only exploring the training set. So if the training set is very large, we can also explore only part of the training set and to make manipulation more easier and faster. In our case, the test set is quite small, so we can continue working on the full data set. And before that, let's create a copy of the train set we created, and let's name it housing and keep the training set aside. So the first step would be to visualize the geographical data. Since there are longitude and latitude data available in our data set, it's always a great idea to create a scatter plot of the district to visualize the data. So this still does that for you, and we are using the plot method of the data frame. What kind of plot we need? That's the scatter. What should be the x-axis? This should be longitude. What should be the y-axis? That's latitude, and also you should provide the value of alpha for it. So if you look at the plot provided here, you can see it's the California districts, and also some of the areas are denser compared to the central parts and also northern part. So our brain is very good at spotting patterns in the pictures, but you may need to play around with visualization parameters in order to gain more insights and to extract patterns from the data. So in order to do that, we can using the same plot method of the data frame, but here we are using the size of the scatters in order to represent the district's population, and also color to represent the price. And the JIT color map is also used in order to differentiate different colors. So if you run this cell, this is what you get. And obviously, when you look at this figure, you realize that, okay, in the Bay Area and also near San Diego, these are areas with more populated district and also higher prices for the higher median prices for the houses.
And also you may realize that, okay, if we go higher, the price would relatively decrease, but these are just guesses. So after looking at this, you may also look at the correlation between different features. Since the dataset is not too large, we can easily compute the standard correlation coefficient, also called the Pearson's R, between every pair of attributes using the correlation method. So this tool does that for you. The correlation coefficients range from -1 to 1. When it's close to 1, it means that there is a strong positive correlation. For example, the median house values tends to go up when the median income goes up. The correlation coefficient is 0.68. When the coefficient is close to -1, it seems that there's a strong negative correlation. You can see a small negative correlation between the latitude and the median house value. That is, prices have a slight tendency to go down when you go north. And finally, coefficient close to 0 means that there is no linear correlation. Next figure, which is provided here, shows various plots along with correlation coefficient between their horizontal and vertical axis. The correlation coefficient only measures linear correlation, as I mentioned, and that's that if x goes up, the y generally goes up or down. It may completely miss out the nonlinear relationship. That is, if x goes, for example, if x is close to 0, then y generally goes up, and vice versa. Note how all the plots of the bottom row have correlation coefficients equal to 0, despite the fact that their axes are closely not independent. These are examples of nonlinear relationships. Also, the second row shows examples where the correlation coefficient is equal to 1 or -1, and notice that it has nothing to do with the slope. For example, your height in inches has a correlation coefficient of 1, while with your height in feet or nanometers. Another way to check the correlation between attributes is to use the pandas scatter matrix function, which plots every numerical attribute against every other numerical attribute. Since there are now 11 numerical attributes, you would get like 121 plots, which would fit in the page. So here I'm limiting the number of features to median house values, median income, total rooms in house, median age. And this is the plot shown. So if you look at each plot, for example, here, it's showing on the x-axis shows the median house value, and on the y-axis shows the median income, and then apparently there's a relation between these two. Or if you look at the median income versus median house value, it's really promising because it shows that as the median income goes higher, the median house value also goes higher. And on the diagonal plots, you can see the histogram of that value, which is similar to what we plotted earlier. So the most promising attribute, as I mentioned, is to predict the median house value. For prediction of the median house value is the median income. So let's zoom a little bit at that and explore it. So this plot clearly reveals a few things. First, the correlation is indeed very strong. You can clearly see the upward trend and the points are not too dispersed. Second, the price cap that we noticed earlier is clearly visible at horizontal line at $500,000 here. But this plot also reveals other obvious straight lines. One of them is probably here, the other one is here. And these can stop your model from learning, but we will look at the result and then we will have a better idea. So in order to prepare the data for the machine learning algorithm, instead of doing it manually, we can write the functions for this purpose, and there are several good reasons for that. One is that this allows us to reproduce this transformation easily on any data sets. Also, we will gradually build a library of transformation functions that you can reuse in future projects. You can also use these functions in your live systems to transfer the new data before feeding it to our algorithm. And finally, this will make it possible to easily try new transformation to see which combination of transformation work best. But first, let's revert to clean turning data by copying train set again. And let's separate the predictors and labels, since we don't necessarily want to apply the same transformation to the predictors and the target values. So we simply can use the drop in order to drop a median house value from our train set. And also we can call the median house value column and copy it. And I call them housing and housing labels. Housing is our feature, includes our feature, and housing labels the target, the median house value. So next step would be to clean our data sets. And as I mentioned in the previous session, most of the machine learning algorithm cannot work with missing features. So we need to create a few functions to take care of this. We saw earlier that the total bedrooms attribute has some missing values. So we need to fix this one. We have three options. One is to get rid of the corresponding features. The other one is to get rid of the districts with missing values. And finally, we can set some values for missing data. And that is usually setting them to 0, the mean of that feature, and also the median. So these can be easily done with drop NA, drop, and fill NA methods of the data frames, pandas data frame. The first option, that is to get rid of the corresponding district, just drop NA and select the column you want to, or the feature you want to get rid of. Second option, which is to get rid of the whole attributes, we can call the method and call the axis. It will drop axis equal to 1, which drops that column. And finally, we can calculate the median of the total bedrooms and fill the missing values with median using the fill NA method. And this is very easy with pandas data frame. Also, if you noticed, we had categorical variables, which was ocean proximity. There were like 5 options for the ocean proximity: less than 1 hour to the ocean, in the Bay Area, on the island, inlands, and close to the ocean. So almost none of the machine learning algorithm can deal with text like this. So one thing we need to do is to convert this text into numbers, so our machine learning algorithm be able to deal with this data. Here I have provided the 10 first instances of ocean proximity. You can see that there are repetitive values. It's not arbitrary text. There are a limited number of possible values, which each of them represent a category. So this is called the categorical attribute. That is, the number of cases that our instances have are limited to 5, 6, 7, and numbers like that. So most of the machine learning algorithms, as I mentioned, prefer to work with numbers, and we should convert this text into numbers. For this purpose, we can use Scikit-Learn's ordinal encoder. So simply import from Scikit-Learn preprocessing the ordinal encoder, create an instance of the ordinal encoder, then feed and transform your housing categorical variable to it, and then we can see how that works. So instead of the text, now we get a list of categories using categories instance variable. It is a list containing a 1D array of categories for each categorical attribute. In this case, the list contains a single array, since there's just only a single categorical attribute. And this is equivalent to these values: ocean, inland, island, nearby, and near ocean: 0, 1, 2, 3, and 4. So one issue with the representation is that machine learning algorithms will assume that the 2 nearby values, for example, 1 and 2 in this case, are very similar than 2 which are distant from each other, like 0 and 4. So this may be fine in some cases, so for ordered categories like bad, average, good, and excellent. But obviously, this is not the case for the ocean proximity columns. I mean, the distance between inland and island is not necessarily similar to the distance between island and near bay. To fix this issue, a common solution is to create a one binary attribute per category. One attribute equals to 1 when the category is less than 1 hour to the ocean, and 0 otherwise. and another attribute equals to 1 when the category is inland and 0 otherwise, and so on. This is called one-hot encoding. And because one attribute will be equal to one hot, while the other will be 0 to a cold, so the new attributes are sometimes called dummy attributes. And Scikit-Learn provides a one-hot encoder class to convert categorical variables into one-hot vectors. So in order to use the one-hot encoder, you can simply import it from Scikit-Learn.preprocessing, then create an instance of it. I have called it cat encoder. And we can use housing cat encoder and feed transfer method in order to convert our data into one-hot encoder. So notice that the output is a SciPy sparse matrix instead of a NumPy array. This is very useful when you have a categorical attribute with thousands of categories. After one-hot encoding, we get a matrix with thousands of columns, and the matrix is full of zeros except for a single per row. So using up tons of memory in our system to store zeros would be very wasteful. So instead of a sparse matrix, we can store location of non-zero elements. And by this way, we can save a lot of memories. Also, we can convert this sparse matrix of SciPy into NumPy array using the toArray method. So simply call the toArray, and we can see that it has been converted into a matrix, which at each row we only have one, which shows the value for that. So this is the last step for preparation of the data. Next thing we can do is to select the model and train our model using the dataset we prepared. So for this purpose, it's really easy. Actually, in the previous part of the workshop, we deal with one of them, the linear regression. We repeat that process here again. So we need to import linear regression from Scikit-Learn.linear module, and then create an instance of that module, and then call the feed method using the X, which is the features we're using for predictions, and also the label. And if we run this cell, you can see that easily it's feed a model, and that's all. So we now have a working linear regression model, and now we're gonna try to see how does that work. So I have created some data from housing data and also some labels. The target it should be predicting, and here we can see the results. So for the first example, the prediction is 80,000, 181,000. For the second one is 286,000. For the third one is 263, and labels that it should have predicted are provided here. We can see that there are some errors in our predictions, but we need to have a picture in our mind of how accurate the predictions of the models are. So the predictions are not really accurate, but we should measure using a metric. So here I'm using the RMSE, root mean squared error, on the whole training set using the Scikit-Learn's mean squared error function. So for this purpose, we need to import the mean squared errors from Scikit-Learn.metrics, and then predict the values over the training set, and then call the mean squared error on the predictions versus the labels, and finally get the SQRT, the square root of that, and that's the number, 69,000. This is better than nothing, but clearly not a great score. Most of the districts' median housing values range between 120 to 265 US dollars. So a typical prediction error of 68,000 is not very satisfying. But this is an example of underfitting the training data. When this happens, it means that, as I mentioned, we need to provide more data, more information, or use a model which is more powerful, that is have more parameters. And as we saw in the previous session, we can also do the feature engineering, that is combine our features or do a series of calculations to have better features, to reduce the constraints on the model, to decrease the regularizations, and things like that. So our model here is not regularized, which means that linear regression is definitely not a good option. It's not a good option for predicting the housing values in California. Our next option is decisions tree regressor. It's a very powerful model capable of finding complex nonlinear relationship in the data, and not only for decision tree, but for all the models provided in Scikit-Learn library. It's very easy to implement that. It's very similar to what we did for the linear regression here. You just need to import that model from the Scikit-Learn. After that, you create an instance of that module and finally call the fit. And for predictions, you call the predict. Okay, so for the decision trees from Scikit-Learn, the tree import decision tree regressor, create an instance of the decision tree regressor here, and finally feed that to the X and Y that you provided in your data sets. And finally, when we got that, we need to evaluate over the training sets, and the error is 0. Wait, it cannot be true, right? This is a clear sign of overfitting. The decision tree is not that powerful to capture everything. So it shows that the model has remembered everything and has badly overfit the data. So how we can be sure? What we need to do is to use the technique that we discussed at the end of the previous session. That was to divide our training data into validation sets and then use the cross-validations in order to see how the model is performing over the validation set. So in order to do the cross-validation in Scikit-Learn, you simply need to import the cross_val_score from scalar.model selection. Then you pass your instance to it. You pass the X and Y that are your features and labels, and then you set the scoring, and also CV shows the number of cross validations, number of division of the training set that should be done. And at the end, you can calculate the scores. So if we try the cross validation, the scores are provided here. The mean error is $69,000 and standard deviation is 137. When we compare to the linear regression model, I think that the linear regression model is performing better. So here we saw that the error was 0 on training set, but actually it's not 0. It's like 69,000. So it shows that the decision tree doesn't look as good as it did earlier. In fact, it seems that it's performed worse than the linear regression model, as I mentioned. And notice that the cross-validation allows us to get not only an estimate of the performance of your model, but also a measure of how precise the estimate is. The decision tree has a score of approximately 69,000, and you would not have this information if you just used one validation set. But cross-validation comes at the cost of training model several times, which is costly and needs a lot of time, and also computational sources. If we repeat the process for the linear regression model using cross-validation, we can also see an increase, a little increase in the performance of the model. So it was clear that decision tree was overfitting badly, that it causes it to perform worse than linear regression model. Also, I promised that we will cover the random forest. So this is the last model we are going to talk. The random forest regressor works by training many decision trees on random subset of the features and then averaging their predictions and building a model on top of that models, on top of a couple of models called ensemble learning. And it's often a great way to push machine learning algorithm even further. Random forests are usually not prone to overfitting that much unless your training set is not really well prepared. So in order to use the random forest, we need to import random forest regressor from the scalar.ensemble module. Then we create an instance of the random forest regressor. We need to define a series of hyperparameters like number of estimators, the criterion for feeding, random state, which help us to make our experiments reproducible. We can also set the minimum split, minimum sample leaf,
and other hyperparameters, which you just need to check the Scikit-Learn's user guide, and it's introduce all the hyperparameters and also describe the functionality of them. So these are the hyperparameters that you need to evaluate before processing. After creating the instance, you need to call the feed method. You pass your features, you pass your labels, and it takes a little time. And you can see that the performance of the random forest is much better compared to the decision tree and linear regression. And as I mentioned, random forest is a super powerful model, and it also is a very, very good benchmark if you want to compare your deep learning algorithm with. And if we repeat the process using cross-validation for the random forest, we will see that the performance gets slightly worse, and we expected that. Anyway, the random forest looks very promising, and note that the scores on training set is still much lower than on the validation set, meaning that the model is still overfitting the training set. And the possible solution for overfitting are to simplify the model, that is to reduce the number of parameters our model have, constrain it, regularize it, or get a lot of more training data before we dive into the much deeper into a random forest. However, we should always try many other models from various categories of machine learning algorithms, for example, support vector machines with different kernels and possibly neural networks, without spending too much on tweaking the hyperparameters. And the goal is to shortlist a few models, and then these promising models can be used for hypertuning your results. And finally, after preparing the model, it's time to test it on test set. We tweak our models for a while on the validation set. We eventually have a system that performs sufficiently well, and now it's time to evaluate your final model. What we do is to use the test set. As I mentioned earlier, the test sets at the beginning of our experiment, when we gather the data, we divide it into 3 sets: the training set, which is used to train the model; the validation set is used for hypertuning the parameters; and finally, the test set, which at the end, when your model is hypertuned, you test it over the validation set. And there's nothing special about this process. You just call the predict, and that's it. So we are at the end of our session. If you have any question, please feel free to unmute yourself and ask your questions. If you need to review this, I know that the pace was really high, so if you need to review this, you can read them later on. You have my contact information here. You can text me here or on GitHub page. You can ask questions. And thank you for taking part in this workshop. Any questions?
I was curious about the categorical attribute. And could you show maybe in one of these models how you would fit that back in? You just add it back as a column to the training set?
Yeah, thank you for asking that, John. And actually, if you notice, I didn't include that in the final part. Let me go back to the. Okay, I just converted that as a categorical variables, but I didn't include it in the training data, right? So what you need to do, we got the housing, right? Let me do it in another cell. So first, let's see what our housing data frame look like. Okay, and also we got the housing cat, I think, but with the name of the, no, so let me see what was the name of the variable first. Housing cat 1 height. So we are interested to combine these two, right? The two array. So what you need to do is to call the, for example, NumPy or pandas, doesn't matter. You have a method which is concatenate. You feed a list of what you are interested to concatenate. That's housing from housing and
Perhaps you could put your screen share back up.
Oh, sorry. So can you see the screen now? Can you see the screen, John, now?
Yes.
Okay, so what we need to do is to use the concatenate method from NumPy. Also, pandas have similar thing, and you pass your housing and also the one hot encoded value. And if you call it, I haven't closed it.
You used a subset of rows in your data set, I think, to create that.
Let me see. I need to explore this. Okay. Okay. So let's deal with it in a different way. Stack, restack. Okay, so you can use it with the stack from NumPy. Also, you can do it with concatenate, but you need to define the axis that your dataset should be stacked together. Okay.
So just the lamination access, in other words.
Right.
Would you do that to your test? Would you do that to your test set as well?
No, I didn't include that here. I forgot to mention that, but I didn't include it
Okay.
one hot here in the data set.
Yeah, I'm just trying to clarify it. So I would include it with the test set.
Right.
And then, pardon me if someone else has a question, but the cross validator, could you forgo creating a separate test set? Or would that introduce another form of error that I don't understand?
What do you mean the separate test set?
So for the cross validation score,
okay,
you split up your training set to compute the cross validation score. Could you?
I didn't include the test set here. I used the validation set. Okay. So here I'm using CV of equal to 10. That is to divide the training set into 10 equal subsets. And at each time steps and each trial of the model, it uses 9 of those sets for training the model and calculate the score on one of the remaining one, and continues this process until it has seen all the training instances, and then calculate the average score over the validation set. It's not using the test set here. But if you are interested to calculate the score over the test set, you just need to call your cross-validated model and then use the predict model, calculate the predictions, and then compare it with your test set.
Well, thank you very much. I appreciate that. I had never used Scikit-Learn before, so it looks to be considerably handier than some other alternatives.
But I agree with you. It's I think that it's the friendliest possible machine learning library available out there. And the only library that you can compare with is the Cross, which is used for deep learning. But unfortunately, Cross doesn't support, as far as I know, doesn't support simple machine learning algorithms like decision trees, SVM, and random forest. So the Scikit-Learn probably is the best option available. So thank you for your questions. Any other questions? If no, thank you all for participating in this workshop, and please feel free to contact me if you have any question about machine learning or deep learning, and I would be more than happy to help. Have a good day. Take care. Bye-bye.